Hi everyone, welcome back to another Pre-Calculus 12 video. We are carrying on today with 6.4. We're doing the second half of graphing trig functions, and today I'm going to bring in transformations. So last day we just did a basic sine graph, basic cosine graph, and a basic tangent graph, and I got you to focus on the key aspects on each of those graphs. And today we're going to continue on with those, but we're going to bring in some of this transformation stuff that we learned in chapter 2. So it'll be us putting together some old stuff with the new stuff that you've learned. I will build in a tiny bit of review as well from last day's lesson, and that should hopefully help to make things a little easier to understand. So let's dive in. The first example we have is y equals sine x, which is the same one as we did last day. And just to remind you, if I were to simply graph it out, it's the one that starts at 0 and goes up like that. And we know that this was our point 2 pi. This was our, actually, why don't I color code them like last day? So if this is our 2 pi, this one must be pi, and this one started at 0. And if we take a look at our maximum and minimum points, then that would be at pi over 2, which is our maximum at 1. And this one, whoops, that's not what I meant to do, but that one would be at 3 pi over 2, and that would be this minimum point, which is at -1. So there's a really quick recap of a regular y equals sine x graph. But then we could transform that and we could create y equals a sine of x. I'm going to use the same language that I used when I first taught you about transformations, because I think consistency is helpful when you're learning. So I've always started with this leading question is you would look at this a and you would think, does that affect my x values or my y values? So still ask yourself that guiding or leading question when you're looking at these types of equations. And since the a is in front of the entire sine x, we know that that's going to impact the y value. So that means it's going to stretch it up and down or shrink it up and down. That's the impact that that a value could have on what's going to happen to our graph. Okay, so it's an example of a stretch. That's what the a value does, to refer back to the transformation terminology. So let's take a look on the same graph of what a graph or what a specific example would look like. Like if I wanted to graph out y equals 3 sine x. Sorry, I can change that to 2 just because I realized I didn't draw my graph tall enough to be able to fit in 3. So we can do that. If we have 2 sine x, all that it does is it doubles all of my y values. So the intercepts are going to stay the same because they were at 0. Y value is 0, so this can't change that. But my max and min are going to change. So instead I'm going to have this at 2. And instead, I'm going to have this one at -2. So it takes my graph and it basically stretches it out. So it goes there, there, and there instead. So you can clearly see I've purposely done it on the same graph so you can compare back to our original sine x graph and see the impact that this 2 would have on our graph. And that is simply stretching it. Okay, I do feel like this is kind of review, so I'm going to, just dive right in. The next one is if I instead make this y equals -2 sine x. Well, remember the impact that that negative sign has. The negative sign simply flips our values. If it's in front of this -2 here, then it's flipping the y values. So what that does is instead of this 2 that was up here, it's going to take it and flip it down to, I'm going to do that down here. My intercepts, my 0, pi, and 2 pi, they're going to stay the same. So this point here that I'm coloring in, this point here, if you can see it in pink, and this one here, the starting point, they stay the same. They're unchanged by the a value. But my maximum flips down to -2, and my minimum of -2 now flips all the way up to, whoops, wrong color. It flips all the way up to +2. So instead, I have the opposite thing going on where it's going through the same intercepts, but I have an upside down flipped sine graph. So you get to see the impact that that has. Okay, so basically that little a value, I'm going to write this off to the side, this affects our amplitude. Just to throw in a little bit of review from last day, to get the amplitude, if I'm going to use the purple one here, I'd go to the midline, which is still the x-axis, and if I count all the way up to the maximum, that tells me my amplitude for this one. It would have an amplitude of 2. The first basic y equals sine x graph always has an amplitude of 1. So that's basically some built-in review from last day with a little bit of new stuff with this stretch happening in the a value. Okay, so then if we are looking at the period, so stretching it left or right, again, I'm going to start with y equals sine x, so I have something basic to compare it to. So that would be, again, this basic one that goes like this. That's pi, that's 2 pi, we know this, that's 0. Same old stuff as what I just did up there before I colored all over it. And then that could change to give me y equals sine b of x. Okay, I think in order to really drive this point home, I'm going to do this in a different color. And I'm going to use this as an opportunity to talk a little bit about that. This affects my period because we already know from before. I start with that leading question. Does the b affect my x values or my y values? Since it's right in front of the x here, I know that it's affecting the x values. So I know that it's either stretching it or shrinking it in horizontally. So it's like a horizontal translation. So this would affect the period because that's what we call this one rotation to remind you. So this would be the period, which would be 2 pi in a regular one. I'm going to get rid of that. But so in this case, whatever b value is there, we would have to take that into consideration when determining the new period. And so we have a little formula for that. It's always 2 pi divided by whatever the b value there is. So what does that mean? And actually I should say over the absolute value of b, because the period's always going to be a positive value because we're sort of looking at the distance and not positive or negative. So absolute value, that's the reason that that symbol is there. Okay, so if I still have the same grid that I'm actually going to extend a little bit. No, that was awful. Extended, oh, that's even worse. Whatever, we're stuck with it. So let's say that instead of that, I change this graph to make it, let's say, I'm going to draw it or write it over here. I'm going to do y equals sine of 2x. And I'm choosing yellow so I can show you on the same grid. We know that we would have 2 pi, and then we would also, I'm just going to mark it down about the same distance away. So maybe about there would be 3 pi, maybe about there would be 4 pi. And so we're going to take a look at the impact that this is having. So if I have y equals sine 2x, my period will be 2 pi over 2. So my period is just going to be pi in this case. So I know that it's taking my graph and it's compressing it horizontally. It's shrinking it in. So I basically am going to fill in a full rotation, a full period, and I'm going to finish it here. So everything that's happening gets compressed. So basically at the halfway mark, like there, so at pi over 2, just to be super clear, is where I would actually have my value crossing the x-axis. So I know that my maximum went from over there to sliding over here. So I actually have a graph that now looks like this instead. So from 0 to 2 pi, so I've only drawn one period, but if I were to keep this going, now from 0 to 2 pi, I would fit in 2 periods. But maybe just to visually draw the point, to drive the point home, I will leave just one period there for you to see, because I think if I do two of them, it's going to look a little confusing or misleading when you look at it. So that's the impact that it would have if we had y equals sine 2x. Let's take a look at one that's a little bit different. Let's say instead I had y equals sine of 1/2 x. Okay, so again, I would think, does this affect my x values or my y values? We know it's the x value, so we know it's going to either shrink it or stretch it out. You're smart people. I'm sure that you already know that if 2 had an impact of shrinking it in, then 1/2 is going to stretch it out. But let's do the work to figure this out. Our period would be 2 pi over 1/2. So you can see that we would be flipping and multiplying by that, which means that our new period ends up being 4 pi. When I say flipping and multiplying by that, I'm just being lazy with the words I'm using. All I mean is we would flip and multiply by the reciprocal of this, so it would be times 2 over 1. That's how we got the 4 pi. So I know now my graph is going to end there. And so I also know that this 2 pi is like my halfway point. So that's where my other intercept now is. So basically all the stuff that was happening before, and like pi is where my maximum is going to occur, and 3 pi is where my minimum is going to occur. So it's like this big, long, stretched out version of the sine graph. So you get to clearly see the impact that that 1/2 has on the period of this graph. I want to make this clear. The cosine graph would be exactly the same thing, except with the cosine graph, which is different than the sine graph, just slightly. You'd still take the same approach. You would still do the same thing. Okay, so I can just talk easier if I have some tea. But anyways, so that's the impact that it has on the period. Okay, so now our next transformation, but it has a different name. This is called phase shift, which is just a fancy new way of saying horizontal translation to the right or left. So let's take a look at what that looks like. If we have, for example, y equals sine x, which is always our basic function, but we take a look at the impact that this has, this phase shift, it would be, for example, y equals sine of b, so I'm throwing that in there as well, x minus c. So I am also throwing in a little bit of what I just taught you in the last example, which is a stretch affecting the x values, but then we also have this in brackets x minus c. So I think already by looking at this, you're starting to see the resemblance with all the different functions that we practice transformations with. It just so happens that now we're applying our transformations to trig functions, but it's still the same thing that's happening, still the same rules that we're applying. So let's take a look at a specific example of what this might look like. So for example, if we want to take a look at the impact of y equals sine of 2x minus pi over 2. Whole thing in brackets. Okay, so First of all, this does not really look like this thing that I gave you, but I need it to look like that because we need a nice clean factored form so I can easily pick out what B is and pick out what C is. So that's my first step or my first job in working with this. I need to clean things up and factor out appropriately to figure out what it is that's going on. So let's do that in our first step. Y equals sine. And I need to factor out this 2. I never want to have a coefficient in front of my x there. It always looks all nice and clean, just like the one in the box there. So I factor that out. I'm dividing, to be clear, technical of what we're doing, dividing both of these out. So I end up with pi over 4 when I do that. That's telling me that I would move my graph pi over 4 to the right. To the right. That's the impact that it's having. I know that because there's a minus sign in front of it. If it were a plus sign, we know that we would move it pi over 4 to the left. I also know that this 2 tells me that my period would be 2 pi over b. The b value is 2, so 2 pi over 2 means my period must be pi. So there's the information that I need to use to figure out how to graph this or what it's going to look like. So that's the first couple of steps, is to get that listed so we can start to figure things out. And so when we go to work on this, nothing has happened to move it up or down. So I'm only interested in the impact that it's having moving left to right. So if the period was going to be pi, I'm going to draw out a regular graph and say in a regular graph, and maybe I'll do that just initially like this. I'm going to say that would be pi, that would be -1, and that would be 1, just so we get a sense of what we're working with. So this is not really my answer. This is me just drawing out, just dealing with the period of 2, the b value of 2 that has a period of pi. So I'm just dealing with that part, and now I'm going to look at the impact that this part has. It's being shifted pi over 4 to the right. So to be clear about this, let's think our way through this. In our initial graph, this would be like pi over 2. Then this would be pi over 4 if I think about how this goes. So I'm basically chopping up my graph into quarters, if you can think of it that way. Like there's a quarter, there's a quarter, there's a quarter, and there's the last little bit. So like 1, 2, 3, 4 little chunks or pieces in there. That's what I'm talking about. I feel like the last line is misleading or makes it look like there's 5 parts. So anyways, 4 different parts we're interested in, which are those parts. So I'm just taking it all and sliding it like pi over 4 to the right, or this part here. So I would take this point and it would now be here. This point would now be here. This point would now be here. This point would now be here, and this point would now be here. So my new graph would just look like this. And to be clear, if we're doing fractions over 4, that would be pi, or 4 pi over 4. So this point must be 5 pi over 4. So again, I'm trying to get you to shift to thinking in terms of fractions. Because our phase shift had to do with pi over 4, I try to think of my whole graph in terms of fractions over 4. So good to start to practice that skill in order to be able to make sense of or interpret what's going on here. Okay, so I hope that that's helpful so far. Then we're going to look at vertical displacement, which also is really just like an old thing coming up again. It's just vertical displacement. It's what it sounds like. We're moving it up, like vertical translation up or vertical translation down. So same stuff from our transformations chapter. It just has a new name, and really who cares what it's called. I just want to make sure that you know how to do this or what to do with this. So if we had again y equals sine x, And instead I decide to change that to y equals sine x plus d, for example. Oh my gosh, what am I doing? Sine x plus d. It's Friday. That's my x. Okay, so this part is just a vertical displacement d units up, but if it had minus d, it would be d units down. So really, you see what I mean, that we don't even really learn anything new all year or through the whole course. We basically just take a whole bunch of old skills and tack them on to new functions in each chapter. And these functions happen to be trigonometry, but it's still the same thing that we're doing. So I feel like this one you might find is the easiest one so far. If, for example, you are asked to sketch y equals sine x minus 4. Okay, so I feel like, do we even need to do the basic one? Sure, why not? If we just had a basic, like our starting graph, I'm going to do that really lightly because we don't actually want to use it. Nothing has happened to affect the period or anything. We can just leave it as is, like this. The period would be 2 pi on that. And then all that we're doing, if we have a sine x minus 4, is we're going to take this line, like the x-axis, and we're going to move that down like minus 1, 2, 3, 4, let's say, so minus 4. So I would just take my whole graph and just slide it down to there, but it's all the same stuff that's happening there. It'd be the same graph, but just it slid down 4 units, so it's a little bit lower. All the same stuff that's happening though, to be super clear, that means the max would happen at minus 3. That means the min would happen here at minus 5. And otherwise, everything about it is exactly the same as a basic sine graph. So I just want to show you what it would look like if we, like I've been showing you step by step, isolating one new little thing at a time, which I think is a good way to learn initially what this would be like. But then putting it all together would be y equals a sine of b x minus c plus d. This would be our sine equation with all transformations applied. So just to be clear with this would be like absolute value would be the amplitude. You know what? I did amplitude before in green. Sorry, everybody. Might as well keep things consistent. So this would be our absolute value of A would be our amplitude. So you can start to see the impact that this is having. The period, that would be this B value. So that's going to be the period, which would be 2 pi over the absolute value of whatever's there for B. We talked about that. It's a distance. That's why it's absolute value. And then at this point, I don't even know which colors I used for what, so you're just going to have to deal with whatever I give you at this point. But if we have plus or minus C, that's just a phase shift. This would be C units to the right, but it just depends on what we plug in there. And then I am running out of colors, so we're just going to have to deal with white for that one, but that would be our vertical displacement that we basically just went through, and it would be D units up for whatever that is. D units up, or if I were to plug in minus 5, for example, it'd be 5 units down, so you know, it would just change according to whatever it is we plug in. Okay, so let's take a look at an example. State the amplitude, period, phase shift, and vertical displacement. Vertical displacement of the following. You have y equals negative 2 cos 2 over 3x plus pi over 3 minus 1. Okay, well, that's a lot of stuff happening. First of all, well, I would want you to pause the video right now and actually try this on your own because it's not new. It's putting everything together into one question, which we always do. So try it on your own, hit play when you're ready for the solution, and let's go through this. When I look at this, the first thing that stands out to me is my x is not by itself, and I need it to be by itself. So we need to factor this out. So everything else looks okay though. So y equals negative 2 cos, and I would factor out this 2 over 3, and in brackets, that would leave me with x plus pi over 2. How did I get that? Okay, to be super clear, I would do 2 over 3 divided by 2 over 3, which is just 1, so that pulls that out. But here I would be doing pi over 3 divided by pi over 3, which is like saying times 3 over 2. So the 3's would cancel, leaving me with this. You should know how to divide by a fraction. Try it though. Don't just watch me do this passively. Make sure that you're good with that. And then minus 1. Everything else is the same. We just need to factor out the 2 over 3. So now I'm able to look at this and analyze and pick out the things that I need from here. So it said state the amplitude. Okay, so I know where to look for the amplitude. The amplitude I would get from right here. So I would say that my amplitude is equal to 2 because it's always the absolute value. Because it's a distance. It's not, it's a distance. So we just take the positive of that. And then if we're looking for, what was next? The period. For the period, we know that we would look to this part here. So I would say, I'm just really stressed about the colors, everybody, if you're wondering what's going on here. So if we're, I'm trying to keep it consistent, but it's hard. So if we're looking for the period here, we know that it would be 2 pi over b. So it's going to be 2 pi over 2 over 3. So again, think of it this way. You're dividing by a fraction, so you're actually going to flip and multiply. That's like saying times 3 over, oh, that's not a 3. Times 3 over 2, right? Dividing by 2 over 3 is the same thing as saying times 3 over 2. So you can see that when we work our way through and do that, the 2's cancel, so 3 pi is my period. So that's my period. I feel like this is not the neatest thing ever, but hopefully you're understanding and learning this. And then it asks for the phase shift. Okay, so phase shift, if this is what's given to me, I just read it off of there. The phase shift is pi over 2 to the left because it's a plus 2, pi over 2, and we know it's always the opposite with x. And then when we're dealing with our last one here, that would be a vertical displacement, 1 unit up. No, it's not. It's 1 unit down because it has a negative sign here. Okay, so I hope that that helps you to get some clarity on how to do this. And let's take a look at the period of tangent. Just a reminder that if we have a regular y equals tan x, that the period is always, so the period of that is pi. If I change it to make it y equals tan of bx, then the period here is going to be pi over absolute value of b. So this is just like the other one that we did there. It would be pi over the absolute value of whatever you have there for b. Hopefully, you won't find this too bad because it's pretty much the same thing. The only thing that's changed is instead of 2 pi, it's now just pi. So let's take a look at some examples. If we say determine the period, and I have tan 3x, and I should do it properly. A would be y equals tan 3x, y equals tan of 1/4 x, and yeah, let's do that first and then I'll give you some more. Again, I would want you to hit pause right now, try this on your own, and then hit play when you're ready for the solution. So it's pretty much exactly what it looks like there. I look at this and think, okay, my period is going to be pi over 3, and there's no calculations or anything to do. I just look at it and I interpret it. So that's what we would get. Same thing over here. I would say, okay, my period is pi over, and I'm going to put it in brackets just to, again, drive the point home. If we're dividing by 1/4, it's the same thing as flipping and multiplying by the reciprocal. So when we do that, do you see that I would just get 4 pi for my period? Okay, let's take a look at another one. C and D. That looks like an A. C and D. So if we have y equals 3 tan of 1/2 x, and here we have y equals 1/2, oh, it's negative, negative 1/2 tan of pi over 3x. Okay, so don't let that throw you off. Yeah, this is changing the amplitude, but remember, tan doesn't really even have an amplitude because it's that asymptote one that keeps going up and down. So forget about that. We're interested in the period right now. I know that it would be pi over 1/2. I know that means I just flip it and multiply by the reciprocal. So that means my period here must be 2 pi when I flip it and look for the reciprocal. And same thing here, it would be pi over 3. So maybe for this one, I'll kind of show you, just to be clear, that means we're doing pi times 3 over pi. So the pi's would cancel. So after all that, my period here would be 3. I'm going to write period there as well. Okay, so I hope that that is helpful, and I am going to get you to do numbers 1 to 10. I'm going to suggest all of them, but I understand that's a lot. I've given you a lot this week. So take your pick. Once you feel like you've gotten into the swing of things and you know how to do it, start skipping. So you can do every other question instead. If you feel like you need more work on some of the questions than others, then do all of them for those questions. So I hope you found that helpful.